Good morning, learners and viewers. Welcome to the session for quantitative analysis for managerial application. Today, we will start with Unit 4, that is measures of variation and skewness. First of all, we will start with what is the significance of measuring variation. Measuring variation is significant for some of the following purposes. That is, measuring variability determines the reliability of an average by pointing out as if of how far an average is representative of the entire data. Another purpose of measuring variability is to determine the nature and cause of variation in order to control the variation itself. Thirdly, it is measure of variation enables comparisons of two or more distributions with regards to their variability. What are the properties of good measure of variation? A good measure of variation should possess, as far as possible, the same properties as those of a good measure of central tendency. Following are some of the well-known measures of variation, which provide a numerical index of the variability of the given data, that is range, average of mean deviation, quartile deviation of semi-interquartile range, and standard deviation. So we will discuss each of them one by one. We will start with range. Suppose we range is basically the difference between the highest and the lowest value of the distribution. Here, what we see if we take an example of numbers from 2, 3, 4, 5, 6, 7, 8, 9, 10. So the smallest number is 2 and the highest value is 10. That is the difference. 10 minus 2 is 8. That means we can say that the range is 8. The range is the simplest measure of variability to compute. However, it does not use all of the data. As the sample sizes increases, the range can increase, but the range can never decrease. Here, we take another example how to find out the range does not decrease. If we take an example of 2, 3, 5, 10, so here the range is 8. Now we have increased the numbers from 2 to 10. So here the range is 8. That is the highest value minus the lowest value. Range does not give any information about the nature of the distribution of the values. Another concept is coefficient of range. That is, it is basically a ratio of differences of the highest value and the lowest value to the sum of the highest value and the lowest value. Now we move to quartile deviation. Quartile deviation is also known as semi-interquartile range. It is computed by taking the average of the difference between the third quartile and the first quartile. Its third quartile is represented by Q3 and the first quartile is represented by Q1. That means quartile deviation is Q3 minus Q1 by 2. The relative measure corresponding to quartile deviation is called as coefficient of quartile deviation. That is, it is calculated by Q3 minus Q1 divided by sum of Q3 and Q1. Quartile deviation is superior to the range as it is not based on the two extreme values, but rather on middle 50% of the observations. Another advantage of quartile deviation is that it is only measure of variability, which can be used for open-end distribution. Here, the disadvantage of quartile deviation is that it ignores the first and the last 25% of the observations. Then comes your average deviation. The measure of average or the mean deviation is an improvement over the previous two measures in that it considers all observations of the given set of data. This measure is computed as the mean of deviations from the mean or the median. Here, the deviations are treated as positive regardless of their size. That means here we can see that we are summing up the mod values of the difference between the x and the x bar. X bar here in this case is the mean. If we are taking average deviation from the mean, then we have to apply summation mod value of x minus x bar divided by number of terms. If it has to be average deviation has to be calculated in terms of median. So here x bar is replaced by median. That comes summation of mod value of the difference between x minus median divided by n. The relative measure corresponding to the average deviation is known as coefficient of average deviation. If average deviation has been computed for median, the coefficient of average deviation shall be obtained by dividing the average deviation by the median. There is an advantage in taking the deviations from median because the sum of the absolute deviations from the median will be minimum in actual practice. However, arithmetic mean is more popularly used in computation of average deviation. That means coefficient of average deviation is the ratio of average deviation to median or average deviation to mean. Although the average deviation is a good measure of variability, its use is limited. If one desires only to measure and compare variability among several sets of data. The average deviation may be used. The major disadvantage of average deviation is it lacks of mathematical properties because we are ignoring signs. We are computing by using only positive values. This is more true because non-use of sign in its calculations makes it algebraically inconsistent. Now, the next part is standard deviation and variance. Standard deviation and variance measures variability about the mean. Standard deviation is used in other statistics and is the most stable of the variability indices. If one reports the mean as the measure of central tendency, then the standard deviation is also reported. The standard deviation is good for interval or ratio data. However, standard deviation is affected by extreme values. Approximately 68% of the measurements, that is the data, will fall within one deviation of the mean. 95% falls within the two standard deviations, that is 1.96 mathematically. And in case of 97.7, almost 100% fall within the three standard deviations. The concept of standard deviation was introduced by Carl Pearson back in 1893. In terms of the symbol, standard deviation is basically represented by sigma, and mathematically it is evaluated as under root to the ratio of square of the difference of x from the mean to total number of observations. And in case of crooked frequency distribution, that means if we have frequency in the data, that means that f, that will be the formula will change as under root of summation of f into x minus x plus whole square divided by n. This formula of standard deviation can be written as in other forms also, depending upon the nature of the data or the mathematical application what we are using. We have another relation for this one. So that is sigma is equal to under root of summation fx squared upon n minus summation fx by n whole square. And if we are taking differences of the deviations in our calculation of mean, that means if d is equal to x minus a by I, then x is replaced by d. That in that case, the formula becomes summation of under root summation of fd square by n minus summation of fd by n whole square into I. Remember that this into I is outside the under. And if we talk about variance, it is the square root. It is the square of standard deviation. That is, it is denoted by sigma square. Now, we will see a problem and how this formula, what we have discussed, are applied to a numerical problem. Suppose the table below provides the data for library membership of children in different age groups. We have to find mean and standard deviation of the membership fee. Now, we have age group from 5 to 7, 8 to 10, 11 to 13, 14 to 16, and 17 to 19. Membership fee is given to us, that is for the first case it is 30, 40, 50, 60, and 70. Now, number of children, that is 10, 8, 7, 3, 2. This number of children will be treated as the frequency. Now, for our calculation purpose, we will be changing this. We will be considering age group and number of children as we have discussed that it is the frequency. Now, since the number we are talking about membership fee, that means here we will be considering this membership fee as x. Since the numbers are small, so we won't be using a deviation formula for that. Straight away we will be multiplying 30 into 10 for fx, we will get 300. Similarly, for all values, we will get different values. that is 320, 350, 180, 140. In the last column, we have to evaluate fx square. That means we have to square the value of x. 30 square is 900, 900 into 10 is 900. Similarly, we will be calculating for all the way. We are going to get 5 different values. We have to sum up. Now we will be summing up summation of f, summation of fx, and summation of fx square. Means straight away we are going to get summation of x by n, that is 1290 divided by 30. That is 20. Now we will be using formula for standard deviation because there is no deviation, or since the data was small, frequency numbers were small, so we cannot use any deviation in this. Straight away we will be using summation of fx square by n minus summation fx upon n square. Summation fx square sum is 599 divided by 30 minus 1290 divided by 30 whole square. After calculating, we are going to get standard deviation as 12.15. Now we move to coefficient of variation. For distributors having the same mean, the distribution with the largest standard deviation has the greatest variation. Use different formulas. This coefficient of skewness was derived by Carl Pearson, and he suggested that the measure of skewness can be computed from mean, median, or mode. If we talk about mean and mode, we can use the formula Sk, that is coefficient of skewness, Karl Pearson skewness coefficient, is equal to x minus mo. Mo is mode divided by standard deviation. And if we talk in terms of quaternions, that means we will be using a part of median. In that case, the formula is Q3 plus Q1 minus 2 times of Q2 divided by the difference of Q3 and Q1. Coefficient of skewness, Sk, is equal to 3 times the difference of mean minus median divided by standard deviation. If Sk is greater than 0, the distribution is positively skewed. And if Sk is less than 0, it is negatively skewed. And if Sk is equal to 0, the distribution is symmetrical. Q3 plus Q1 minus 2 times of median divided by Q3 minus Q1. It is the formula for coefficient of skewness which was given by Boole, and it is more appropriate because we use it. Now, here again we will discuss about a problem and we will see what is the difference between Karl Pearson, application of Karl Pearson formula and Boole's method for calculating coefficient of skewness. We have profit in thousands for the and number of companies. So we will convert that information into these columns. That is profit 10 to 12 to 14 till 24. We are given number of companies, that is the frequency, 7, 15, 18, 20, 25, 10, and 5. Here we see that large marks, that is profit number, are bigger and the frequency is bigger. In that case, we will be using different formula. We will be finding a suitable condition to evaluate this problem. So first of all, we will find out the middle value or midpoint. That is midpoint of 10 and 12. It will be 11. And we can see that there is a difference of 2. So we will be adding 2. That 2, 13, 15, 17, 19, 21, and 23. Now, we will count how many observations are there. We can see that there are 7 observations. The center value will be the 4th one. So we can place 0 over there. And above 0, we can place -1, -2, -3. And below 0, we can place +1, +2, +3. Now the question arises how this is evaluated. So at the top, you can see that D is equal to x minus 17 divided by 2. Now, going further, we will calculate FD and FD square. We have to be very careful in calculating FD. We have to consider minus sign in this. We cannot leave or ignore minus sign in this calculation. 7 into -3 is -21. 15 into 2 is -2 is -13. 18 into -1 -18. 20 into 0, 0. And similarly, we will calculate 25, 28, 50. Now, the last column, it is FD square. So we will be squaring D, values of D. So that means we won't be getting any negative term over here because all negative terms, when they are squared, negative sign is converted into plus sign. So we can see that squaring -3 is 9, 9 into 7 is 63. Similarly, we will be calculating all the values of FD square column. Now, we have to sum up summation of F, that is N. Summation of FD, that is -9. Summation of FD square, that is 251. First of all, we will calculate mean. Mean is x bar is equal to A plus summation FD by N into I. Here, A is what we have assumed, that is 17. The summation of FD is -9, which is taken from the table. N is 100 and I is 2, the difference between 12 and 10. After calculating it, we will get mean of this data is as 16.82. Now, we will move further to calculate its mode. Mode is calculated by L plus D1 by D1 plus D2 into I. If you remember, maximum frequency occurs in 25. For mode, we have to see maximum frequency. So here in that case, the lower limit will be 18. So we will be calculating this 18 plus 5 upon 5 plus 15 into 2. I is 2, the difference between 12 and 10. So we are going to get value as 18.5. Now comes your standard deviation. Standard deviation formula is under root summation fd squared by n minus summation fd by n into I. After placing up all the values and calculating, we get standard deviation as 3.1634. Now, we will be using the formula mean minus mode by standard deviation. That comes 16.82 is the mean, mode is 18.5, and your standard deviation is 3.1634. Mode is greater than negative plus. Thereafter calculation, it comes out to be negative 0.5310. As the negative sign is there, mode is greater, so it is negatively skewed. And there is a greater concentration towards the higher profits. Now, for calculating Wolf's skewness coefficient. We have companies say below 50, 50 to 60, 60 to 70, 70 to 80, 80 to 100. And the number of companies are 8, 12, 20, 25 and 50. We have to calculate cumulative frequency. Now the thing is that I don't know how many of you remember how to calculate cumulative frequency. So I will be just brushing up. In front of 8, the first value you write 8, and in 8 add 12, so you are going to get respective value of 20. In 20 add 20, you are going to get 40. 40 plus 25 is 65, and 65 plus 15 is 80. When you are going to sum up all these values of the number of the companies, you will get 80. Now, we have to calculate quantiles Q1, Q2, Q3. Q2 is median. We will start with Q1. Q1, your N is 80. 80 divided by 4. That will give 20th observation. 20 lies between. You have to check this 20 in terms of cumulative frequency. That lies in the class interval of 50 to 60. So here in that case, L will be 50. N by 4 is 20. BCF, that means preceding class cumulative frequency. That means cumulative frequency above 20. That is the observation of the median class is 12. And the difference is 10. So we get Q1 as 60. Q2, N by 2. N by 2 is 80 by 2. That is the 40th observation. 40 comes in 60 to 70. So similarly, we will be using the formula Q. As I told you, Q2 is median. So we will be calculating L plus N by 2 minus BCF by F into I. L is 60, N by 2 is 40, BCF 20, and frequency of the median class is 20, and the difference is 10. We get 70. Similarly, we will be calculating Q3. In that case, we will be using 3N by 4. Formula remains the same, but for Q1 it is N by 4, for Q2 it is N by 2, and for Q3 it is 3N by 4. So we get 670 plus 60 minus 40 by 25 into 10. After calculation, it comes out to 10 here. We know the formula is Q3 plus Q1 minus 2 times of median upon Q3 minus Q1. Raising up all the values, we get negative 0.11. In Boley's method, we got negative 0.53. This value of coefficient of skewness indicates that distribution is slightly skewed to the left, and therefore there is a greater concentration of sales at the higher values than the lower values of the distribution. And for Carl Pearson method, we got negative 0.11. This value of coefficient of skewness indicates that the distribution is negatively skewed, and hence there is greater concentration towards the higher of it. Now, what is quartile deviation? Quartile deviation is basically the difference between Q3 and Q1 divided by 2. The relative measure corresponding to quartile deviation is coefficient of quartile deviation. That is Q3 minus Q1 divided by Q3 plus Q1. We know how to calculate Q3 and we know how to calculate Q1. The quartile deviation is superior to the range as it is not based on the two extreme values but rather on the middle 50% observations. Another advantage of quartile deviation is that it is the only measure of variability which can be used for open-end distribution. And the disadvantage of quartile deviation is that it ignores initial 25% and the last 25% of the observation. Average deviation, it is denoted by AD. It is sum of mod values of difference of x minus x bar, that is mean, divided by n. And if we talk in terms of median, it is x minus median by n. Theoretically speaking, there is an advantage in taking the deviations from median because the sum of the absolute deviations from median is minimum. Now, we move to block 2, which comprises of probability and probability distribution. We have 4 units in that. We will start with what is the basic concept of probability. Probability is concerned with random experiments. Here, data demand and inference to be drawn, and statistical inferences are never certain. Statisticians will be prompted to use prefixes or suffixes as likely or at almost likely. They're not sure. What is the basic concept of probability? Probability and its concept are thus very important to interpret the inferential statistics. The theory of probability is a study of random experiments. In random experiment, set of all possible outcome is always known, but it is not possible to predetermine the outcome. For example, the probability of a coin toss resulting in either head or tail is 1. The probability of coin toss resulting in head is 1 by 2 because the toss is equally as likely as result is tails, and there are only 2 possible outcomes. Probability deals with calculating the likelihood of a given event occurrence, which is expressed as a number between 1 and 0. An event with probability 1 can be considered a certain event, and an event with a probability of 0 can be considered as an impossible event. Or in other words, with the help of probability, we can assign a measure to the uncertainty with the occurrence of each possible outcome in a random experiment. What's this probability of getting a red card from a pack of cards? If we talk about basic theory probability formula, probability of a successful event is favorable cases upon total number of cases. And in red, in a pack of cards, we have 26 red cards, and the total number of cards are 52. The probability of mathematically, the probability of getting a red card from a pack of cards will be 26 divided by 52. That is half. Now, what are the basic terminologies what we use in probability? First of all, it is the experiment. The term experiment is used in probability theory in a much broader sense than in physics or chemistry. Any action, whether it is tossing of a coin, measurement of a product's dimension to ascertain its quality, or the launching of new product in the market, constitute an experiment in the probability theory terminology. Then comes sample space. The set of all possible outcomes of an experiment is defined as sample space. Each outcome is thus visualized as a sample point in the sample space. That means in a toss of a coin, there are two possible outcomes, either a head or a tail. This means that is the sample space. Event. An event in probability theory constitutes one or more possible outcomes of an experiment. That means an event can be defined as a subset of the samples that is a part of it. The experiment is a toss of a coin. Sample space is either tails or head, and the event is getting a tail on a toss. Now, moving further, we will find out what are the different definitions for probability. We have two basically used conditions, that is classical definition of probability, and the second one is axiomatic definition of probability. Before defining probability, several other definitions need to be understood. That means we will start with the random experiment. An experiment or trial which whose outcome is not perfectly predictable, but for which the set of all possible outcomes is repeatedly trial is known. That means if we take up an example of toss of a coin, we know that either a head or a tail will come. That means we have two outcomes. Then a random variable is an assignment of numbers to possible outcomes of a random experiment. For example, if we consider toss of a coin, but that is a simple example. The number of heads showing when the coin lands is a random variable, and number of tails is given by t. The random value assigns the number 0 to the outcome pt, 1 to the outcome th, and 2 to the outcome head of both. The outcome space is the set of all possible outcomes of a given random experiment. The outcome space is often denoted by capital S. An event is a subset of outcome space. An event is determined by a random variable. Outcomes are the set of all possible results of a random experiment. Then comes your exhaustive events. Exhaustive events are a set of events in a sample space such that one of them compulsorily occurs while performing the experiment. Or in simple words, we can say that all possible events in a sample space of an experiment constitute exhaustive event. For example, while tossing an unwise coin, there are two possible outcomes, head or tail. So these two outcomes are exhaustive events, as one of them will definitely occur while flipping that coin. Disjoint or mutually exclusive events. Two events are disjoint or mutually exclusive if the occurrence of one is incompatible with the occurrence of other. That is, if they can't both happen at once, if they have no common outcome. Eventually, two events are disjoint if their intersection is an empty set. independent event. Two events A and B are statistically independent if the chance that both happen simultaneously is the product of the chances that each occurs individually. Now, knowledge that one event has occurred does not give any information whether the other event has occurred too. That means we will discuss. See an example. Getting head on the first throw and getting head on the second throw are two independent events. Then comes your equally likely events. Two events are said to be equally likely if the occurrence of none of them is expected in preference to others. Equally likely events are those events which have an equal probability of occurring. For example, when we toss an unbiased coin, the probability of getting a head is 1 by 2, and the probability of getting tail is again 1 by 2. So we can say that it is an equally likely event. When we roll a die, the probability of getting 1 is 1 by 6. Probability of 2 is getting again 1 by 6. Probability of 3 is 1 by 6, and probability of getting 6 is 1 by 6. Here this is another example of equally likely event. However, the probability of drawing one red ball in a bag of three blue and two red balls is 2 by 5. The probability of drawing a blue ball from a bag of three blue and two red balls is 3 by 5. We can clearly see that these events are not equally likely to occur. This is basically what is the difference what we get. Now, mathematical definition of probability. If n is the number of equally likely, mutually exclusive, and exhaustive outcome of a random experiment, out of which n outcomes are favorable to the occurrence of an event A, then the probability that A occurs is denoted by PA, and PA is the ratio of number of outcomes favorable to A upon number of exhaustive outcomes. Mathematically, we can say that m by n. All these approaches, however, share the same basic axioms. These axioms are fundamental to probability theory and provide us with unified approach to probability. The axioms are: the probability of an event A, which is denoted as PA, must be a number between 0 and 1, and both are inclusive. That means we can say that probability of any event is 0 is less than or equal to PA is less than or equal to 1. Second one is the probability of occurrence of one of the other of all possible event is equal to 1. If S denotes the sample space of the set of possible events, we write PS is equal to 1. That means summation of getting a tail or a head 1 by 2 plus 1 by 2 is 1. If two events are such that occurrence of one implies that the other cannot occur, then the probability that either one or the other will occur is equal to sum of their individual probabilities. What we have discussed, probability of head plus probability of tail is 1. Now, we will take up a problem which is somewhat a bit under complex situation. In a survey, it was found that 21 people like product A, 26 like product B, and 29 like product C. If 14 like product A and B, 12 people like product C and A, and 14 people like product B and C. And there are 8 people who like all the three. Now the thing is that how many people like product C only? This problem is basically related to the application of set theory. We'll see how it is used. We have three products A, B, C. We will go back to the problem. So we will be converting this information what is given to us in the problem to in the mathematical form. Na is equal to 21, Nb is 26, Nc is 29, and N A intersection B. That means 14 people like product A and B. That is intersection. 14. And C intersection A is 12, and N B intersection C is 14. And all the three is like by, that means it is denoted by N A intersection B intersection C is equal to 8. Now, when we convert this information into a Venn diagram, so we see that we have three products, we have three circles. These three circles will be intersecting. When we go back to the condition what is given to us, here we can see that N A intersection B is 14, 6 and 8. And C intersection A is 12. 8 is included over there and 4 is here. And for B intersection C it is 14. 8 is already included and we get 6. And A intersection B intersection C is 8. At the center we get 8. Now, how to calculate how many people like product C? Product C, here we can see that it is 29. So from this 29, we will be subtracting 4, 8, and 6. We get 11. That means there are 11 people who like product C only. Another problem, we consider your locality where out of 5,000 people residing, 1,200 are above 30 years of age and 3,000 are female. Out of the 1,200 who are above 30, 200 are female. Suppose after a person is chosen, you are told that the person is a female. What is the probability that she is above 30? So we see that there are two conditions in the problem. First condition is that a person who is chosen is above 30. And the second case is that she is a female. Now the thing is that going back to the last statement of the problem, if after a person is chosen, you are told that the person is a female, what is the probability that she is above 30? That means we can see that event A has occurred. Event A has to be considered in the condition that B has occurred. If we denote that event by A, we want to find probability of A by B. Out of 1,200 persons who are over 30, 200 are females. That means, and out of a sum of 5,000 people in the locality, 200 possesses the characteristics of being female as above 30. Since event A and B can be defined as events that a person is both a female and above 30 years of age, if we choose A as a person chosen is above 30 years and B a person chosen as a female, that means in terms of probability we are going to get BA as 1,200 to 5,000, BB 3,000 to 5,000, and probability A and B, that is 200 by 5,000. To find the probability, that the given a female has been chosen, she will be above 30. We see that out of the 3,000 females in the population, only 200 females are above 30. That means A by B is 200 by 3,000. We have to calculate BA by B. In that case, 200 by 3,000 can be written, and that is the answer what we are being. Now the question is how it is being calculated, or what is the another way of calculating it. Here we can see that 2,000, 200 by 5,000 into 5,000 by 3,000, which we in the other term can be written as 2,000 by 200 by 3,000. That means PAB by PB. In axiomatic approach, probability is introduced as a function of outcomes of an experiment under certain restrictions. These restrictions are called axioms of the probability. We have seen that axiom first one is that the probability of an event is a non-negative real number. That means it will be between 0 and 1. Probability axiom 2 is the second axiom implies that the probability of an event that is certain to occur must be equal to unity. How do we assign probabilities to event? There are few theories on probability which will help us in mathematical treatment of the subject of probability. Now, mathematically, while solving the problems, what we will be using. So, the first is probability of null event is 0. If PA bar means negation of A, the negation of A is 1 minus PA. Third theorem is B A negation intersection B is BB minus BA intersection B. Now these values will be given to us in the problem. If we talk in terms of addition of probabilities, A union B is equal to PA plus BB minus BA intersection B. Conditional probability theorem, that means A intersection B. It can be written in two forms, PA into B by A or PB into BA by B, where PB by A is a conditional probability of B given that A has already occurred. Theorem 6 is multiplicative theorem for independent events. If A and B are independent events, then the probability of their occurrence simultaneously is given by P A intersection B is equal to PA into PB. Then comes the most important part, that is the Bayes theorem. Before starting it is required to know about prior and posterior probabilities. Prior probabilities are the probabilities which are assigned to events on the basis of conditions or past experience or judgment. And posterior probabilities are the revised probabilities in the light of some additional information. Because this is much more important when we apply Bayes theorem. If it states that if A and B are two mutually exclusive and collectively exhaustive events, and C is another event defined in the context of same experiment, then given the values of PA, PB, PC by A, PC by B, the conditional probability that PA by C will be equal to PC by A into PA upon summation of PCA into PA plus PC by B into PB. If we talk in terms of B and C, the B part will come up and the denominator will remain the same. Now we take up an example. A car manufacturer manufacturing factory has two plants, X and Y. Plant X manufactures 70% of the car and plant Y manufactures 30%. 80% of the cars of plant X and 90% of the cars at plant Y are rated of standard quality. A car is chosen at random and it is to be of standard quality. What is the probability that it came from plant X? Now we see that there are two plants manufacturing cars. They are manufacturing quality products. Respected probability is given to us. We are selecting a car of standard quality. Now, what is the probability that it came from plant X? Now, we will be converting this statement to our mathematical form. Let A be the event of the car is of standard quality. B1 and B2 be the events that the car is manufactured by plant X and plant Y. Going back to the problem, 70% of the cars are manufactured by plant X and 30% by plant B. That means 70 by 100. B1 is 7 by 10 and B2 is 3 by 10. Now, event is of the standard quality. If it is manufactured by plant 1, so it will be PE by B1. It is 80 by 100 given in the problem, 8 by 10. And car selected is of standard quality and it is manufactured by plant Y. It is 90 by 100, that is 9 by 10. Now, our problem is what we have to find. We have to find the probability of us selecting a standard quality car, but it is manufactured by plant X. Mathematically, how we will be changing this? We have to calculate PB1 by E. That is equal to PB1 into PE by B1 upon summation of PB1 into PE B1 plus PB2 into PE by B2. Now, we have PB1 as 7 by 10, PE by B1 as 8 by 10. In the denominator, we will get these values plus selecting of plant and their respective quality manufacturing probability, that is 9 by 10. We are going to get 56 by 83. If, just moving further, if we have in the same condition for the same problem, now the problem is we have to calculate the probability that a standard car has been chosen and it came from plant Y. So what we are going to change? In case of B1, we will be using B2, and in case of in the numerator, and denominator will remain the same. The answer will be 27 by 83. Now, we move to discrete probability distribution. If all the possible outcomes of an experiment together with their chances of occurrence were made available, these are the conditions. If betting on heads, you find that a toss of 3 coins may result in 0, 1, 2 or 3 heads with the respective probability of 1 by 8, 3 by 8, 3 by 8 and 1 by 8. We'll see it, how we get these values. This representation of all possible outcomes and their probabilities is known as probability distribution. If you are interested in finding out the numbers of heads in tossing of 12 coins, you need to apply a discrete probability distribution. Discrete probability distribution is used or can be used in decision making. Outcomes of toss of 3 coins are expressed in terms of number of heads. What we are going to get: no head, 1 head, 2 head, or 3 head. And Respectively, we will be getting the probability of the occurrence. This uncertain real variable h, which assumes different values depending on the outcomes of an experiment, and to each of whose value a probability assignment can be made, is known as random variable. A discrete probability distribution counts occurrences that have countable or finite outcomes. This is in contrast to the continuous distribution, where outcomes can fall anywhere in the continuum. Common example of discrete distribution includes binomial, Poisson, and Bernoulli's distribution. A discrete probability distribution function has two characteristics. Each probability is between 0 and 1 inclusive, and the sum of the probabilities is 1. Discrete events are those with a finite number of outcomes, that is, tossing of a dice or tossing of a coin. For example, when we flip a coin, there are two possible outcomes, that is, either head or tail. But when we roll a dice, we get an outcome 1, 2, 3, 4, 5, 6. In that case, if we have to compute mean, the mean will be summation of x into bx. X is the event and bx is the probability of the event. The variance, that is sigma square, and standard deviation sigma of a discrete random variable are numbers that indicate the variability of x over numerous trials of the experiment. Now, we will see what are the different terms what we use in discrete probability distribution. On the left side, we have probability that we were talking about x, 0 head, 1 head, 2 head, or 3 head. These are the discrete values. Distribution of number of heads, that means ph, what is the probability of getting a head? That is 0.125, 0.375, and 0.125. This is the probability distribution. And your random variable is distribution of number of heads. Now, a description given the value of a random variable along with the corresponding probability is called probability distribution of the random variable. If a random variable x takes the values of x1, x2, x3 till xn, and the respective probabilities is p1, p2, p3 till pn, mathematically we can convert it like this. Now, above probability distribution of x is defined only when each probability is greater than or equal to 0, and summation of the probabilities is 1. For mean and variance of random variable are calculated as mean is equal to mean equal to ex, which is mathematically equal to summation of xi pi. Variance is sigma square is equal to summation of x square I pi minus mu square, that is mean square, and your standard deviation is the under root of variance. Variance is defined as the expected value of the square of the difference between the random value and its expected value. With this, we will be concluding today's session and we will be continuing with this in our next session.